Here's kind of a gussied up version of the lecture on Monday. I had some technical difficulties, but we've worked most of those out. So I'm going to start pretty fast because it's reviewing what's already on another video. But the key to fermions and the unfortunate indistinguishability of Juan and Clarissa that fortunately is responsible for the complete existence of the universe, life, and everything as we know it, is that if I take two identical objects that are fermions and I exchange them, so I'm looking at the wave function psi as a function of the total coordinates of object 1 and object 2, that has to be equal to the negative of the wave function psi of object 2 and object 1, if I just interchange those objects. And we can represent that in terms of quantum numbers, like we always can, and I use the bracket notation here, that I'm going to break up the spatial part of the set of the wave function and the quantum numbers, and the spin part, because they're really quite strictly separated from each other. So we've got n L m sub z for object 1, n L m sub z for object 2, m sub s, the orientation of the spin for object 1, and m sub s for object 2. And just to be explicit, the purple ones are for object 1, the red ones are for object 2, and as wave functions, we can represent this as psi 1 and psi 2 and zeta 1 and zeta 2, where psi is the spatial part of the wave function. I put a little extra tail there because we're kind of using psi for the total and the spatial wave function. And that minus sign again, we have to have that exchange symmetry, and so it has to be antisymmetrical with respect to exchange. But to get that from a spatial and a spin wave function, the point again is that I can have the spatial wave function, now we'll call it again psi 1, 2, all those spatial coordinates, that can be symmetrical or antisymmetrical with respect to exchange. It has to be one or the other. I flip them, and I've either got to get the same wave function back or the negative of the wave function back. But I get the choice because that's true for zeta as well. It can be antisymmetrical or symmetrical, and notice I've written it in the other order, because one of the two of them, and only one of the two of them, has to be antisymmetrical, and that's just because minus times plus equals minus. We're just ensuring that we get a negative sign when we do the full exchange of both the spatial and the spin wave function. And again, that's vitally important because of the way the spin works out. So with the spin, the symmetrization is really easy to visualize, and you really can just look at it. So the up and the down are clearly symmetrical, because both of the two electrons have the same orientation. It doesn't matter which way I represent them. I can't tell which is which. But it's equally true that if I have up and down, that just plain looks different from down and up. You can see that when I exchange those two, that's not the same. And so to make that antisymmetrical with respect to exchange, we really need to have the up-ish and the down-ish pointing exactly opposite each other, and then I can't tell the difference. If I exchange them, I've got one up in the other direction, one up, down in the other direction, and they push me, pull you to nothing. And so that is something that has a total spin of 0. And the other possibility for making them nice and antisymmetrical is have them going up and down kind of in succession. And that is a situation where the z component of the total spin angular momentum is 0, but the total spin angular momentum itself does have a length, and in fact the total spin, the quantum number there, is 1, and that's true for all three of those cases. And so mathematically, this comes to taking the up and the down, the alpha and the beta, and taking plus or minus of the exchange down and up. So mathematically, that's the key, that's the formula we always use, but when I have a positive sign, that's when I get this up and down but aligned with each other version of the up and down that is part of the symmetrical spin exchange wave function. So in all three of those cases, up, down, and up and down but pointing in the same general direction, the total spin is 1. There's 3 of them, like there always is for a total angular momentum of 1, because it's 2 angular momentum plus 1. Total is 1, and I can have a z component of plus 1, 0, or minus 1, and that's what we get. Whereas for the antisymmetrical situation, the total spin is 0, and they are anti-aligned, and there's only one of them because the total spin is 0 and the z component is 0, and there's just one of that. So that is the triplet and the singlet again. They're defined by the spins. So again, if we look at the spatial exchange wave function, it is the spatial exchange wave function that drives the difference in energy. The spin is the one that makes it a singlet or a triplet. Okay, so the spin is the one that defines how many states there are when we have the triplet state or the singlet state. But the spatial exchange wave function is the one that makes the difference with energy. And again, I maintain that it's obvious, since R12 is the vector difference of the position of electron 1 and the position of electron 2. If I exchange the two electrons, I get negative R12. That vector turns around, and that's a minus sign in vector world. And so the issue is what happens when R12 goes negative. And so if I look at the spatial wave function with respect to R12, the central thing here is that because Juan and Clarissa hate each other, electrons 1 and 2 will never be found exactly on top of each other, and so the wave function will go to 0 at R12 equals 0 as circled here, and there will be some maximum, and if this is sort of an S lowest energy orbital type situation, we don't expect a 0 crossing, and so we expect the wave function with respect to electron exchange, with respect to this R12 coordinate, to look something like the green function shown here. And the issue is, how do you draw a symmetrical and an anti-symmetrical function? And you draw a symmetrical one with respect to exchange by doing the same thing in a mirror image. And so we get the orange there. And so that symmetrical spatial exchange wave function has got to pair up with an anti-symmetrical spin exchange wave function to get the overall anti-symmetry, and that's going to be the singlet. So this double-humped camel thing is going to be the singlet, and its energy is defined by its behavior in this spatial exchange over here. Now, for the anti-symmetrical spatial exchange one, I'm going to have the negative sign, so it looks like that. That's the anti-symmetrical exchange one. We've got a peak and a valley. Kind of looks like a 0 crossing, but the negative R is kind of, sort of not real. It is, but it isn't, and sorry, it's quantum mechanics. But in any event, that's the anti-symmetrical exchange wave function. It goes negative when we do the exchange and drive R12 to a negative value. And that is anti-symmetrical, so it has to pair up with the symmetrical spin exchange, and the symmetrical spin exchange is the triplet case. So the anti-symmetrical peak and valley one, or valley and peak one, in blue and green is the spin triplet case. And then the key is when we look at the curvature here. So the one with a cusp, the symmetrical one, has much, much higher curvature. Another way to put it is, even if we call this a node, a cusp is like a node on steroids. So a cusp is even worse than a node, because right at that 0 crossing, the cusp has infinite curvature, whereas right at that 0 crossing, the node has 0 curvature. So the node has low kinetic energy at R12 equals 0, whereas the cusp, the symmetrical exchange wave function, has infinitely high kinetic energy right there. And the way I like to think about that is, in the symmetrical case, in each case, Juan and Clarissa are going to avoid each other. They're going to tend to have the probability of finding them exactly on top of each other is going to be exactly 0. But the anti-symmetrical situation basically gets that for free. To be anti-symmetrical, I've got to go through 0 at R equals 0, and that will be an inflection point, so my curvature will be 0 there. It just has to work out that way. And so it's automatically true that Juan and Clarissa are nowhere near each other in that case. And there's no kinetic energy associated with it. Whereas in the symmetrical situation, Juan and Clarissa more or less actively have to avoid each other. There's very high kinetic energy associated with the avoidance. And so the symmetrical spatial exchange wave function has higher total energy than the anti-symmetrical spatial exchange wave function. And since the symmetrical spatial exchange wave function is paired up with the anti-symmetrical singlet spin function, that means the singlet case, the spin singlet, is going to be higher energy than the spin triplet, which gets that anti-symmetrical spatial wave function. So all else being equal, if I'm looking at identical single electron functions, then the spin triplet case is going to be lower total energy than the spin singlet case. The triplets are always lower in energy than the singlet. Now the all else being equal is a very important caveat here, because the case where the lowest energy is a singlet is the case where I have a filled orbital. If I have a filled orbital, I have no choice, because in this case the spatial function has to be symmetrical. So since the spatial function is symmetrical, then I have to have the anti-symmetrical spin zero case for the lowest energy one, because it's better to push the electrons into the two of them into the lowest energy orbital than it is to fuss around. This business with the spatial symmetry and anti-symmetry is important, but it's nowhere near as important as actually getting the electrons into the lowest energy orbitals possible. So in that case, when I have a filled orbital, I am going to have a singlet S type overall configuration. But if I have unfilled orbitals and the same electronic spatial wave functions to play with, then the singlet is going to be higher in energy than a corresponding triplet. There is no corresponding triplet to the ground state filled orbital case. So that's basically that there. Oh, and we write this thing as singlet S, and I've been specifying that it's a singlet all the time, right? And so we're going to start to introduce the term symbol here, and the singlet should make a lot of sense. But in fact, what we're writing on that symbol there is the spin degeneracy. So we write the spin degeneracy as a superscript before a big capital letter. And that S, that capital S, is just like SPDF, but it's actually referring to the sum total of the orbital angular momentum. And if I have two electrons in a 1s orbital, neither electron has any kind of orbital angular momentum anyway, because the 1s single electron orbital has no orbital angular momentum, and so I'm pretty much guaranteed that my total orbital angular momentum is going to be 0, and SPDF, S is the first one, that means it's a 0, but we make it capital when we're referring to the total orbital angular momentum. So we call this thing a singlet S in the ground state.